So now we're going to begin our coverage of types of Java synchronizer capabilities. And this is split up into two parts. And this will elaborate on things we've talked about before, but do a deeper dive in the context of Java classes and so on. So these are the things we're going to talk about. We're going to talk about the first two in the first part and the second two in the second part. We're going to talk about atomic actions, which are actions that can happen all at once or not at all. Mutual exclusion, which allows concurrent access and updates to shared mutable data without allowing for race conditions. That's what we're going to talk about here. We'll talk about the other two in the next part. So there's all these different capabilities. Let's start off first with the first one, which is atomic operations. And we'll talk about atomic ordering. So atomic ordering is a synchronizer family, a synchronizer capability that ensures an action happens all at once or not at all. Good example would be a transporter beam. If you're a Trekkie, if you're a Harry Potter fan, it would be like disapparating. You want to make sure that you do these things atomically. You don't want to beam half of someone somewhere. That wouldn't be good. Let's take a look at an example that will illustrate the issue here. So this example has two threads, thread 1, thread 2, and we want to have, first we're going to show how you can have problems. So in this particular case, we can have thread 1, which initializes some shared field to 0. Thread 1 reads that field, increments the value by 1, and then writes the value back. Thread 2 reads the value, increments it by 1, and writes it back. This is a sequential ordering, and all is well. However, this sequential ordering will not happen, except by luck, if you don't use synchronizers. If you fail to use synchronizers, then weird things will happen. We'll take a look at that. Ordering is supported in various ways. The way we're going to focus here is by the Java atomic package. And you have to be facile with the Java atomic package for assignment 1B, because you're going to write something called a non-reentrant spin lock using Java's atomic package. Atomic ordering is also supported in a somewhat more limited way by Java's Volatile type qualifier. And the Java Volatile type qualifier ensures a variable is read from and written to main memory and is not cached. So think of it as, do not pass go straight to jail, do not collect $200, just go there, get the value, read it atomically, or write to it atomically. That's what a volatile does. The other approach that we're going to talk about is mutual exclusion, which is a little bit more generalized than atomic ordering. Atomic ordering works on one thing, like an integer, or a long, or a Boolean, or something. Whereas mutual exclusion can be used to prevent simultaneous access to a shared resource in a critical section, which can span more than one thing. So we talked before about how we're going to use mutual exclusion to prevent race conditions from occurring where multiple threads are crashing into the same mutable shared state. And let's take a look at an example that will illustrate the problem. So this is kind of related to what we looked at before, but now we're going to have a problem here. So let's say we have these two threads, thread 1, thread 2, in this field. So thread 1 initializes the field. Thread 1 reads the field. Thread 1 then increments the field by 1 and writes the field back at exactly the same time that thread T2 reads the field. And because they're two threads on two cores, they literally could occur at exactly the same time. And so the question that you have to think about, and this goes back to Java's memory model, is what's the value of the field? Does thread 2 get 0 or 1 when it reads it at the same time that the thread T1 is writing it? And the answer is, we don't have the faintest idea. And that's because this is what's called a read-write conflict. In the absence of synchronization, there's no telling what the value thread T2 will find when it reads what thread T1 is writing to at the same time. Two operations have a read-write conflict if at least one of them is a write. Let's take a look at write-write conflicts, which is another variant of this. Same basic scenario. We come along, thread T1 reads the value of the field, thread T2 reads the value of the field. Thread T1 increases the field's value by 2. Thread T2 increases the field's value by 1. They both write back at the same time. what is the value of the field? Is it 1? Is it 2? What is it? Well, the answer is, again, we don't know, because there's a write-write conflict, which occurs if two threads try to write to the same field concurrently. The result may be inconsistent because it's a race to see who got there last. So whoever gets there last will be the one whose value is stored in that field. And we don't want to write code that's randomly right or wrong, randomly correct. We want code that behaves deterministically with respect to the values of the data. This can yield what's known in the art as a lost update problem. So the lost update problem means if this guy writes back 2, but the other guy wrote back 1 later, then the update is lost. These problems used to be largely theoretical back in the day when computers only had one core and one CPU, because there was only ever one thing really going on. There was no caching. With modern multi-core processors, with the weak memory ordering semantics, which Java's memory model supports, you end up with all kinds of weird problems, read-write conflicts, in the absence of synchronizers due to out-of-order load and store operations that the processor is providing. And here's a simple example of this. This is showing main memory with volatile and non-volatile fields in it. And then we have 3 threads, T1, T2, and Tn. And we've got each thread has its own cache. Each core has its own cache, I should say. And let's say, in this case, thread 1 writes 7 to the non-volatile value. And thread T2 reads from the non-volatile value. And thread N writes to the non-volatile value. And that all happens at the same time. What on earth is cache 2 and thread T2 going to have? It's anybody's guess, right? So that's the problem in context. And synchronizers are there to avoid these problems. Mutual exclusion is supported by Java's locks package. So Java util concurrent locks, which supports reentrant lock, reentrant read-write lock, stamped lock, etc. Mutual exclusion is also supported in Java via the synchronize keyword using Java built-in monitor objects. And you can see here that you can synchronize at the method level, you can also synchronize at the statement level, and so on. And we'll talk about all these things in a lot of detail. So that's the end of the overview of Java's synchronizer capabilities for the first part.